In this video, we're going to talk about Lagrange multipliers with two different constraints. Now, Lagrange multipliers is a really powerful tool for optimizing multivariable functions. And one of the reasons it's so powerful is that we can deal with multiple constraints like we'll do in this video. So we're going to try to understand how this works. We're going to see an example and try to look at both the algebraic side of that example as well as the geometric side of the example, so we can have a nice visual interpretation of what's going on. So the first thing to note is that what we're trying to do is we're optimizing a function f of x, y, and z equal to 0. You can have more variables than that if you so wished. But in addition, we have these two different constraints, g1 and g2 equal to 0. And the idea is it's the maximum of f subject to the fact that these two different constraints must be 0. Okay, so let me try to have a bit of a visual representation. I'm going to draw a generic surface that represents the surface that you get when you set g1 equal to 0. And then I'll set some other surface, and this is going to be the surface representing that g2 is equal to 0, and the first one was that g1 was equal to 0. Now, if I take two planes and I intersect them, what you get is a line of intersection between those two planes. At least this is generically what you get, unless the two planes, for example, don't intersect at all, in which case you can't optimize subject to both constraints. Or if they sort of lie directly on top of each other, you maybe have a whole plane then of intersection. But ignoring those fringe examples, two planes are going to intersect in a line. And then similarly, two surfaces, when you overlap them, are going to intersect along some curve here. The exact shape of it, I don't know, I'm just sort of drawing representatives. Again, these surfaces could sort of align directly on top of each other, or they could not intersect at all. But the generic type of intersection, the one we're going to focus on here, is indeed an equation of some curve. Okay, so now imagine you're sitting at some point on that curve, because what does the curve represent? It represents solutions to g1 and g2 equal to 0 at the same time. So what we're really trying to say is optimizing f subject to the fact that you live on this intersection curve. Now if I'm at some point on that intersection curve, there's actually a couple relevant vectors. The first one is the normal to the g2 surface. And that normal vector can be given by the gradient of g1. Indeed, we've seen this before, that the gradient of a level surface or a level curve is normal to that surface or that curve. This is a level surface. It's a g1 equal to 0. It's a level, if you will, of the function g. Likewise, I can have another normal that sticks up over here somewhere. This is going to be the gradient of g2. Okay, so now really what I want to do here is try to find a way to write down some equation for Lagrange multipliers. And I think the way I want to begin is remind you of what the equation was for a single variable function. Namely, what we say is that the gradient of f is lambda to the gradient of what at the time was just a single constraint that we called g, but here I'm going to call it g1 because we have two of them. Now, in the introduction video, you can go into the entire geometry, really try to argue why this equation was to be true. But basically what we had argued was that the gradient of f was just going to be parallel to the gradient of g. The difference now in the two constraint case is that if I take the gradient of g1 and the gradient of g2, that this is going to generally form a plane. There's the plane that is sort of spanned, to use the fancy linear algebra term, but what I just mean is all linear combinations of the gradient of g1 and the gradient of g2, all ways that I could go some amount in the g1 direction and some amount in the g2 direction. So in other words, these two different vectors are going to define a plane, and that plane is normal to the curve. So, well, previously the gradient of f was going to be parallel just to the gradient of one of the curves. Now the gradient of f is going to be parallel to this linear combination. So in other words, lambda of the gradient of g1, but then I add to that this second parameter mu times the gradient of g2. And then I still have to have that g1 is equal to 0 and g2 is equal to 0, and collectively those three equations give me my Lagrange multiplier system of equations. Okay, so that's the idea. That is the system of equations that we're going to try to go and study. So perhaps let's see how we can use this in a specific example. So my example is that I want to optimize the distance from the origin out to any points that are on the intersection of two different constraints. One, z squared minus x squared minus y squared is 0, and the other, x minus 2z minus 3 is equal to 0. So The first thing you might note is, where is the function I'm trying to optimize? Where is the f of x and y? And the idea here is that this is implicit in the distance to the origin part. And I'm going to say that the normal distance function, at least if I square it, is x squared plus y squared plus z squared. So if I want to minimize the distance, well, it's the same thing as minimizing the distance squared. And distance is given by the formula square root of x squared plus y squared plus z squared. So there sort of is an implicit function. F of x, y, z is x squared plus y squared plus z squared. This is representing the distance squared, and that is the thing I'm going to optimize. And then I still have the two different constraints. I have the g1 here, and I have the g2. That was given explicitly in my problem. So now I just need to take those different things and plug them into this formula that we have, that the gradient of f is lambda times the gradient of g1 plus mu times the gradient of g2. Now the point about this first equation is that it's a vector equation. Gradients are vectors. They have three different components. The first is the partial with respect to x, the second the partials with respect to y, and the third the partials with respect to z. So because there's these three different components, the first equation is really three different equations, three different scalar equations at least. So let's try to do that. Let's try to write them down in turn. So first one is I'm going to look at the top equation, the gradient of f, but I'm only going to do the derivatives with respect to x. So if I look at my f, then the derivative of f with respect to x is 2x. And then I write lambda, and then the partial derivative with respect to g1 here is going to be minus 2x. And then I add to that a mu, and the partial derivative of g2 with respect to x is just 1, so I'll just leave it. So that's my first equation, and I'm going to call this equation number 1. Okay, equation number 2, I want to take the partial derivative with respect to y now, so it's going to be a 2y. This is lambda times a minus 2y. And then there's actually no y's at all in the g2, so there's nothing in terms of the mu. Then for my third equation, I'm going to have a 2z is lambda. Well, the partial derivative with respect to z is now, then the partial derivative of g1 with respect to z is 2z. Then I add mu times the partial derivative with respect to z of the g2, which looks like a minus 2. And then finally, the fourth equation I'm going to have is still the z squared equals x squared plus y squared. That's just sort of rearranging the g1. And then for 5, it's just the g2. So maybe I'll write this as x is equal to 2z plus 3. I just sort of slightly rearranged. It doesn't really matter. At this point, the problem is sort of done, except for algebra, although the algebra turns out to be important. And we also want to interpret this geometrically at the end. If all you cared about was the answer, you could go and program this into a software package and it would just solve this equations and just give you the values. But let's actually go through the process once, because they're actually nonlinear equations, and 5 nonlinear equations can seem a little bit complicated. What I really want to do to try to solve this, I want to find what is the x, y, and z. I may also find the lambda and the mu. I don't care if I find those values or not, but I'm interested particularly in the x, y, and z. Well, I want to scan through this list and see if there's any equation that's easy to me. And I actually think that number 2 here is the easiest of them, because number 2 has a y on both sides. And so one way that this equation could be true is that y was just equal to 0. And then if y was not 0, the only way you could align these things would be if your lambda was equal to the value of minus 1. Okay, so that sort of gives me my 2 different cases, and let's try to sort of proceed with that. So I'll say that case 1 is the case where lambda is equal to minus 1, and I'm just going to sort of proceed through the computation doing that. All right, so if I do that, then I basically get a new equation 1, which is going to be 2x, and then I'm going to have a minus 1 times a minus 2x, so equal to 2x plus mu, and that's going to imply that mu is equal to 0. And then if I look at the third equation here, so now I know what the 2 different results are going to be. This is going to give me that 2z is equal to minus 2z plus 0. And that's only possible if z is equal to 0. Okay, and then if I look here at the fourth equation, if z was equal to 0, then this is going to imply that x and y are both actually equal to 0 as well. And this point clearly doesn't work. For example, if I go and looking at the third equation here, you get 0 is equal to 0 plus 3. So this whole case 1 is just not possible. Okay, so moving right along, let's maybe now look at case 2. I'll sort of do it up here if you prefer. From equation 4, it really simplifies. This is now just z squared is equal to x squared plus 0. It's the same thing as saying that z is equal to plus or minus x. So then if you look at equation 5, for the case that z is equal to positive x, then really just what we're getting is saying that x is equal to 2x plus 3. In other words, we have a value of x equal to minus 3. Or for the case that z is equal to minus x, then you're going to be getting that x is equal to minus 2x plus 3, and that's going to imply that x is equal to 1. I've already now figured out the y components and the x components, and z's going to follow immediately. So I'm going to really say that there's going to be two cases. There is the point where we have 1, 0, minus 1. And we have the point where x was, what was it going to be, minus 3 and 0, and minus 3 happened when it was the same value, so minus 3. Those are my two different points. I've gotten 2 points, and basically what I've done is, following the magic of Lagrange multipliers, it spat out 2 different points that are extrema to this distance function constrained to these 2 different curves. Well, extrema can either be maximums or minimums, so I guess I should see which of these is the max and which of these is going to be the minimum. So let's do that first. If I take my function value of 1, 0, minus 1, and recall that my function was going to be the sum of the squares of the components, so this is just 1 squared plus 0 squared plus minus 1 squared, so this is going to be equal to a value of 2. And so the distance, which is the square root of this thing, is the square root of 2. If I take the other point, then f of minus 303 is equal to, well, 3 squared, or minus 3 squared rather, plus 0 squared, plus 3 squared, which is equal to 18. And then if I want to say what is the distance, because the distance is the square root of that. Remember, we did the square of the distance in our analysis. Okay, well, square root of 9 is 3, and then there's a final root 2, so 3 root 2. So the idea here is that 1, 0, minus 1 corresponds to the minimum value. This is the closest point on the intersection of those 2 constraints to the origin. And then at the point minus 303, you have a distance of 3 root 2, which is the furthest point away. To help us visualize what's going on in this problem, I'm going to use a tool called GeoGebra, which is a wonderful tool for students to get familiar with graphing different plots and seeing how things go on. I'll leave the link to this particular GeoGebra down in the description. Now, what I'm going to do is go in and type in different equations. And for instance, I have these 2 different constraints, so let's try to write them down. The one constraint that we had was that z squared is equal to x squared plus y squared. Now that I finished typing it, I get this 2 different cones. The top cone is like if I took the square root of both sides, I get a positive square root of x squared plus y squared, and the bottom cone would be the negative square root of x squared plus y squared. Okay, so that was one of our constraints. I'll hit enter so I can now come up with a second equation. I'll put in my other equation. This one was going to be z is equal to x minus 3 divided out by 2 if I rearrange it. And now that's an equation of a plane. Now the point is, to say that I am satisfying both of these constraints is to say that I'm satisfying sort of the intersection of these 2 different surfaces. Which if I visually look at it, it looks like this nice little ellipse that we have down here. That is the intersection of this double cone with the plane. Okay, so now I'm trying to optimize some function given these 2 different constraints. And I'm going to have a sort of nifty trick to do it. So now the question says, I want to minimize the distance from the origin out to, well, this intersection. I know the exact coordinates algebraically, but visually you can see there's a closer point on the ellipse and there's a further point on the ellipse. Now, one trick we can use to help this visualization is recall that we were trying to study x squared plus y squared plus z squared. That was our distance squared, and that's what we were minimizing. But x squared plus y squared plus z squared equals a distance squared. It's just the equation of a sphere. So what I'm going to do is I'm going to write x squared plus y squared plus z squared. And then I'm going to do something really nifty that GeoGebra quite likes, which is I'm going to put a parameter a, and I'm going to write that squared. Now, let me just change the color here to, say, yellow to make it a little bit more visually obvious. Sounds good to me. Now, notice what GeoGebra has done here. It's taken this x squared plus y squared plus z squared equal to a squared, and it's created this little slider here. And as I change the value of a, I can even press this play button to make it go automatically. It gives me spheres of these various different radii. So the point is, I'm asking, at which point does this sphere the radius of that sphere equaling the distance from the origin out to, the periphery of the sphere, at what points does that intersect with this intersection curve, this ellipse? So if I press pause at a spot like this, well, this sphere is too small. It doesn't intersect the ellipse at all. If I go all the way to the extreme end here, this sphere is too big. It doesn't intersect the ellipse at all. It's entirely outside of it. But if I time this just right to something like, how about right about there? Well, this just barely touches the ellipse. This radius of this sphere is just coming such that it just kisses the first point on the ellipse. If I make it a little bit bigger, I can try to see if I can time it into the very last point, maybe about there. And so this spot here, this is a sphere of a particular radius, so 4.2 in this case. You can check, that's pretty close to the 3√2 that we computed earlier. We can type that in exactly to get the exact answer. But nevertheless, this is the furthest point along the ellipse where the sphere is still intersecting with it. And if I was to make the sphere bigger, it would no longer intersect with it. So this is my interpretation of this problem using spheres to help visualize minimizing the distance.